There is a video. Let me start over. Take two. There is a computer program called graphical analysis. And graphical analysis is a program that we used in our labs when we did the motion labs, and it's an app that you've used on your iPhone. There's some things that we can do with it that I find really cool. And if I think they're cool, then I'm sure everyone in the entire world thinks they're really cool, because I'm kind of an influencer like that, so it's just kind of something, it's just part of my life. It's not really that big a deal. You don't need to be like impressed. But, oh, you can't see. So it can do some cool stuff. And some of the cool stuff that it can do, besides just collecting data from our lab, we can actually analyze videos. So when we go through, well, I guess let's take a step back. A video. If I pull up my camera and I take a picture, right, one. If you hold that button down, you can do like a photo burst, and it takes a bunch of photos. And then you gotta delete them all, right? But if you were to swipe through those photo bursts really fast, what would it look like? Right, that'd be really fast, right? So I can't flip them that fast. Maybe some other people maybe could flip them that fast. It would almost look like a video. For me, it probably would look more like a strobe light. You know, like when you're at high roller skating in the street. Wait, you got high roller? Was that a thing? High roller was not a thing for you guys? Do you even know what I'm talking about? No. So high roller was a skating rink, a roller skating rink. It was where the Quick Trip on Birch and Schofield Ave? I think it's Schofield Ave. Right there, like right where the car wash is, there was this big skating rink, like indoor roller skating, and it was the best birthday place you could have as a kid. Because you'd roller skate and you get pizza and popcorn and soda, and they had like carpet on the walls, so when you ran into the walls it wouldn't hurt quite so bad. It was awesome. And then like they got fancy and like inline skates became a thing, but you had to be pretty good to be on inline skates. Oh, I was gonna say, how did I get there? But at high roller, every now and then they'd put a strobe light on. And then you were like, you know, you're in grade school. But you're like, oh yeah, this is awesome, because then you'd be like, you know, you do like that strobe light. It is cool. Anyways, same thing with like homecoming dances probably. It looked like that, right? You're taking that photo burst, and you flip it as fast as you can, your hand's gonna kind of go like that. And what it does is it just takes a whole bunch of pictures that are a certain time interval apart. And that's what a movie is. Except for instead of us having to flip it, it flips it automatically for you. So if you know the frame rate of your movie, and you play it back at the same frame rate, then it looks like a nice movie. If you play it back slower, like let's just pretend I took 5 pictures every second, you'd have like every 1/5 of a second, you'd have like some jerkiness, right? So if you go more frequently, it becomes more smooth. A typical camera frame rate on your iPhones, if you were to go into your settings and look, probably your camera is set at probably 60 frames a second. Maybe 30, but probably most of yours are at the 60 settings. Okay, which means that it takes 60 pictures every second of video you take. 30 is going to be lower quality, 60 is going to be higher quality. It's going to be smoother. Okay, so the idea is we can go through and we can take a picture, and then we can take another picture, and another picture, and another picture, and another picture. We call it a movie then. And as long as we know the frame rate of our movie, we can then have a time interval. We can determine time. Mythbusters, you guys ever watch Mythbusters? It like got canceled for a while. I think they shot like a cannonball into someone's house, and then they kind of shut down production for a while. And then it started again. I think they canceled it again. I don't really know. Grant, I believe. Yeah, one of the people from the show died, and I don't remember. That was this year, I think, was it? Yeah. So, but I'm not sure the current state of. I saw like some pop-up ad for Mythbusters in my computer the other day, It was people I did not recognize at all, so I don't know if someone else is taking over the show. I really have no idea. But they use it in Mythbusters. They use a high-speed camera, and they talk about, oh, let's look at this under the high speed. And the reason why they use a high-speed camera is they can make some pretty good measurements in distances, and then they can determine times. So I don't have the high-speed camera like Mythbusters do, but we do have, in most people's pockets, we have phones that can take like 120 to 240 frames per second slow-mo videos. Your iPhones, if you change the settings, I think anything since iPhone 5 can do 120, and somewhere in there they changed to 240 frames a second. Now, I used to have people go through and do this video analysis, and they take a ball and they throw up the ball into the air. And now this is slow-mo, right? So we're playing back it at a slower speed. Now the nice thing about that is we can go through and we can kind of track the ball a little bit better. We can also we had them just take the ball and they drop the ball. And then they could make some measurements. And the computer program would go through and they would plot position versus, no, this is not for those two videos I just showed you. This is the third one that I have. We could plot position versus time, because I could physically take my mouse and I could click on the ball, and then it would advance at a frame for me. And I could click on the ball, and it would advance at a frame for me, which is really annoying when you're taking 200 frames per second. So we'd kind of cheat and say, well, when I click on it, let's skip 10 frames, and then click on the ball again, and another 10 frames. And we can get some motion graphs like this. And then for motion graphs, position versus time. And you can say, well, how in the world do they get position and how do they get time? Because if your camera shoots at 240 frames a second, every frame that we go past is 1/240th of a second. We know a time interval. So if I skip 10 frames, I just fast forwarded 10 240ths of a second. So where's the time piece? Because it's position versus time. So in all those two videos, as well as this video, you might see something in common. The brick wall outside our windows. No, this is no longer here. This is the exterior doors. That probably would have been right about here. Right where that kind of door out in the hallway, that's where those like exterior doors were. And then there was a greenhouse. I don't know if you guys were even here with a greenhouse. That was before they put on the addition. Okay. Maybe when you were sophomores? Were they working on that when you guys were sophomores? Yeah. Okay. So that's where this is. But it's room 220, 221. Look, it's. There, I'll put it back in the window. Okay. So, but this is a 2D motion problem. Oops, spoiler alert, 2D motion problem. And we can take the ball and we can throw it, and again, it's playing back at slow speed. And we could adjust the playback speed of this, but we can go through and the ball goes through the air. Boy, that looks like a certain math shape that we've talked about. And it's a parabola. Okay, it's parabolic in nature. Okay, did you say hyperbola? No. Okay, parabola. Okay, it's a parabola. So it's parabolic in nature. It's a 2D motion, projectile motion problem. It's parabolic. And what we can do, and there's a thing that's in common in all three of these videos, and it's these boards. Those boards are leaning back there. They're a known length board. And in some of those like crime, like CSI, I don't know, what NCIS, any of those crime shows, there's sometimes you'll see like, oh, that's a glove, obviously, or duck footprint. I'm not really sure. Okay, handprint, glove, something. There's something at the scene of crime, and they will take these like little black and white grids, and they'll put it next to it, and they'll take a picture. And you'll see them doing Mythbusters sometimes. They kind of have a grid laid out, and it's so we can take direct measurements off of these to set our scale. That's exactly what this board is. And the cool thing about graphical analysis is it like sets pixels and say from here to here is X many pixels, and they can kind of set the scale that way. So then when we go through and we click on the ball, it's taking measurements, distance measurements for us. Okay, great. When we go through and we click through this ball, we can get through the motion of this object, and this is in the Y direction. The blue is Y, red is X. The ball is in my hand, it goes up to the max height, and then it comes back down and hits the ground. And you might be saying, well, what's going on in the Y direction? Or I'm sorry, the X direction. The idea is, how far is it from my zero reference point? Well, it's getting further away, further away, further away, further away, further away, further away as time increases. That's what's going on. So, to kind of review, motion graphs. A position versus time graph. These are position versus time graphs. It's position versus time graph in the X direction, red. Position versus time graph for the blue, in the Y direction. The slope, hopefully you remember this, the slope of a position versus time graph gives us the velocity. The slope of a position versus time graph gives us the velocity of that object. So if we look at the red line, we can even put in a linear regression line. To say, like, how well does that line actually match? So this box that I'm dragging right now is for the red. And you can say, hey, look at that line. That's a pretty straight line. Tell me about the slope of that line. Is it constant or changing? The red line. Is it positive or negative? Positive. So because the slope tells me velocity, we can say this object is moving at a constant velocity in the positive direction. Now, what does constant velocity tell us? Well, 1D motion sheet, the object is moving at constant velocity, we could say the acceleration is 0. Okay? So some conclusions from that red line is we can say the velocity in the X direction is constant, and the acceleration is 0. Straight line, constant velocity, acceleration. If we take a look at that blue line, this line right here is the best fit line for this blue line. And I hope you say, that does not fit very well. You're right, because it's a parabola, and trying to draw a straight line through a parabola is not a good choice. Okay? But if we say, well, what's true about the slope of this line? Is it constant or changing? It's changing, right? And what about from here to here? Is this slope positive or negative? That's positive. What about over here? Negative. So what happens is it was going in the positive direction, it was going up, and now it was coming down. My slope was changing, which means my velocity was changing. So in the y direction, my velocity is changing, which means my acceleration is not equal to 0. Some other value is not 0. That's all we can really conclude from here. So then what we can do is we can switch this, and we can say, what about the x velocity and the y velocity? I'm glad you asked. And we can go through, and we can look at something like that. We can put linear regression lines, best fit lines. And remember, the red is the velocity in the x direction. Now I'm just going to make up numbers. Here's 5, 4, 3, so I'm going to say that's 3.5. This line's at 3.5. So here's like 3.7, 3.6, 3.5, 3.5, 3.5, 3.5, 3.5, 3.5, 3.5, 3.5, 3.5, 3.4, 3.4, 3.4, 3.5, 3.5, 3.5, 3.5, 3.5, 3.5, 3.4, 3.5, 3.5, 3.6, 3.5, 3.4, 3.5, 3.6, 3.6, 3.5, 3.4. And the basic idea is you can say, boy, those numbers are really, those velocities, this is velocity, straight off the x-axis, those are pretty constant. 3.5, 3.6 are relatively constant. And the slope of that line is essentially 0. We say that's relatively flat. It's not perfectly flat, it's relatively. So we can say it's essentially 0. So we can draw that same kind of conclusion from the velocity versus time. The thing that's more important is if we look at that blue line, this is now velocity in the y direction. The velocity in the y direction from here to here is in the positive direction. Then it stops, max height. And then here to here is moving in the negative direction. It's coming back down. But throughout the motion of this, no matter whether it's going up or down, the velocity and the acceleration in the y direction is constant. Because the only force acting on it is gravity. So no matter which direction it's moving, the acceleration in the y direction is going to be, this data is negative 9.56. We're saying it's essentially, I'm saying, it's essentially 9.8. We can drive gravitational acceleration. It's not perfect, because my video is not perfect. My clicks weren't perfect, but it's close. Okay, so we can go through and we can look at motion graphs and we can say, so what's going on with 2D motion? This is a 2D motion problem. This is called a 2D projectile motion problem. In a 2D projectile motion problem, we can say the velocity is constant in the x direction and the acceleration in the x direction is 0. In the y direction, we're going to say my velocity is changing and the acceleration is negative. That's where some of these things that we're going to talk about today come from. So what is 2D motion? I'm glad you asked. All right, 2D motion. Let's first start with the obvious. What's 1D motion? You guys ever watch the Flintstones?
Yeah.
So there's a cartoon. They're a modern Stone Age family from the town of Bedrock. They're a page right out of history. It's from the theme song, by the way. So Fred and Barney, Fred would go bowling every now and then, and he'd have like this before he bowled, so that's why. Oh, I didn't get it. It's okay. That was 1D motion. The ball was moving in 1D. Okay, it was moving in one direction. One direction. One direction. Oh my gosh, I love that band. You do too? So do I. You know that one song? No, I don't. Wasn't it One Direction?
Yeah, One Direction.
Yeah. Middle school, right? Oh, that would have been like your middle school days? Okay, that was 1D motion. So the ball went straight. 1D motion. That's 1D motion. We could go 1D motion. Okay, that's 1D motion. 2D motion. Fred Flintstone. Kind of looks straight in the video. I don't know. Now, if we define the tiles, these lines in the tile, this was my x coordinate system, this is my y coordinate system. It was moving in both, right? Let's try that again. We're going to change the camera angle. Sam, your shoes are in there, just for the record. It's fine, I'm just telling you. Whoa, look at that! Okay, that's 2D motion. Don't worry, everyone. I don't think I got anybody's face in there except for this one. So, all right, that's 2D motion. 2D motion. It was moving through the x coordinate system and the y coordinate system simultaneously. So what that tells us, if we were to take a stopwatch, now we're to time this. Okay, time this, okay? No, just count. Okay. Okay. And you time you got the x, you got the y. Okay? Perfect. Yeah, perfect. Look at that 2D motion. Oh, Jesus, it's not even there. All right, stop. Okay, and how long did it take to go in the x direction?
4 seconds.
How long?
4 seconds.
4 seconds. And in the y?
2, 4.
4. Good. 4. Wow. Imagine that. They moved this way for the exact same amount of time that it moved this way. Okay? Our time interval were the same. Why? Because it occurred simultaneously. called a 2D motion. Okay, so problem types. It could be a 1D motion problem. And how in the world would you know if it's a 1D motion problem? You know it's a 1D motion problem, yellow sheet, picked up from the bag, also linked electronically as a PDF form. You know it's a 1D motion problem because the object's only moving in the X or it's only moving in the Y direction. Okay, so it's either moving in the X direction or the Y direction, but the key word is or. Okay, so it's a 1D motion problem if it's moving in only the X or it's moving in only the Y. And then if it's a 1D motion problem, trying to get as much on there as I can. Do we need the if part? Careful, coming in high. Holy cow, you're gonna break someone's ankle.
Thanks, Mark.
Yeah, I treated it more like a soccer ball. Oh, Sam!
Mark, is it your fault?
Don't worry, we're okay, everyone. I saved it.
Unacceptable, man.
Oh.
Awesome round.
I got a close-up view of my eyeball on that one, I think. All right, so 1D motion, you either make a list of X or you make it a list of your Y variables. It's one or the other. Okay, it's one or the other. Now, 1D motion was the last unit, so we aren't going to do a lot. There's a few times like, hey, just remember 1D motion, but our new unit is very creatively called 2D motion. Okay, so 2D motion. Oh, and if it's a 1D motion problem, then you really want to reference this. Yours is yellow, I think. You want to reference your 1D motion. Okay, now your 2. If it's a 2D motion problem, and how in the world would you know if it's a 2D motion problem? Well, you'd know it's a 2D motion problem because the problem describes an object moving in two directions simultaneously. My amazing bowling demonstrations were my best attempt to show you a 2D motion problem. That's moving in both the X direction and the Y direction. You say, I thought that was X and Z. Sure. We can define them however we want. If you want to call it Z, okay, fine. It's still moving in two planes at the same time. So as long as it's moving in two dimensions at the same time, it's a 2D motion. But they have to be, it's moving simultaneously, right? So then we make two lists of variables for both the X and the Y axes. X and Y axis. Okay, now notice there is a slight difference in my list of variables. The slight variations is it's not just VI, I call it VIX. It's not just VF, it's VFX and it's AX. It's VIY, VFY, AY. So we're adding another subscript just to clarify that it's my initial velocity in the X direction. It's my initial velocity in the Y direction. It's my acceleration in the X. It's my acceleration in the Y. They are simultaneously occurring, so when we timed how far it went in the X, the bowling ball moved left and right, as well as how long it took to go vertically, amazingly, they were both exactly 4 seconds. And the reason it was the exact same event, right? So they're occurring simultaneously. So my times in both columns are going to be the same. That's the only thing that is the same in these two columns. It's the only thing that's the same. So my amazing bowling ball demonstration, trying to curve it and make it hook, that's a 2D motion problem. We don't do a lot of those 2D motion problems, just for the record. Most of our 2D motion problems that we deal with are a special type of 2D motion problems. And I already showed you a video of a 2D motion, different problem type. It's this one. Great cinematography, I know. The one where I threw the ball through the air. That's a 2D motion problem, but it's a special type of 2D motion problem. The special type of 2D motion problem is called projectile motion. So here's an example of a 2D motion problem called projectile. Okay, this is a projectile motion problem. The ball is moving through the x direction and the y direction simultaneously. It's a 2D motion problem. But it's also a projectile motion problem. So because it's a 2D motion problem, we make two lists of variables. But because it's a projectile motion problem, then there's some more information we can fill in. Now, how do we know it's a 2D motion, projectile motion problem? How do we know it's projectile? So it's a projectile motion problem if, so this says projectile motion problem, okay, I'm just trying to get it big enough that we can kind of see something. We know it's a projectile motion because the object is moving freely through the air in both the x and the y direction. Freely is in quotes, and we'll talk about why in a second. So it's moving freely through the air in both the x and the y direction. And if it's a projectile motion problem, which is a type of 2D motion, then we can conclude that my acceleration, ax, this says ax equals 0. I'm going to post a picture as soon as class is over. I'll take a picture, I'll insert it into today's agenda too, so it'll make it a little easier to see. If it's a projectile, then my ax is equal to 0. And that means my vix and my vfx are equal to 1. So it says vix is equal to vfx. And then it says, use equation number 3. And you say, that seems kind of familiar, right? Because right here, it says the object is moving at constant velocity, and if that's the case, my acceleration is equal to 0, which means my vi is equal to my vf, and then it says use equation number 3. Now some of you say, why equation number 3? Here's why. Here's equation number 3. Delta x is equal to vix. Notice how I added the subscript x to it. Delta x is equal to vix times t plus 1/2 at squared. Ax t squared, sorry. But because my ax has a value of 0, 1/2 times 0 times t squared is 0. This whole back term cancels out. It's a good one to use. When I take this ball, projectile motion, we say, hey, what forces are acting on this ball after it leaves my hand? After it leaves my hand, the force is not strong with me, so therefore I'm not using any Jedi mind powers. And only gravity, right? So what direction does gravity pull? And only down. And what's the acceleration due to gravity on Earth's surface? Negative 9.8, down at 9.8 meters per second squared. That's why my acceleration in the y direction is equal to negative g. On Earth, g has a value of negative 9.8 meters per second squared. But it's not affecting in the x direction. Gravity's not pushing this thing left and right. So you can say, well, what force is acting in the x direction? And if you say not air resistant, ignore it, then you're right. Then there are no forces. So you can say, well, why freely? Because it relates to the exact same term that we used here. Is it a free fall problem? We know it's a free fall problem if gravity is the only force acting on the object. Gravity is the only force acting on this object. Therefore, it's technically a free fall problem. This is a free fall problem in 2 dimensions. That's a type of projectile motion. Now there's 2 types. I'm sorry, that's a type of 2D motion. There are 2 types of projectile motion. There is something called a horizontal launch problem. Okay, a horizontal launch problem. And in a horizontal launch problem, the object is thrown horizontal to the ground. Example, a ball rolls off the table, a ball is thrown flat, or the car drives off of a cliff. Those are all examples of a horizontal launch. And if it's a horizontal launch, then we can conclude, or we can add to our list of variables, that my VIY, my initial velocity in the y direction, has a value of 0. If it's a horizontal launch, which is a type of projectile motion, and projectile motion is a 2D motion problem, so it goes 2D, projectile, horizontal launch. That's kind of the sequence of these. 2D projectile horizontal launch. Then we can say my initial velocity in the y direction is 0. Okay, so if I take this ball, and I roll it off, if I take this ball and I roll it off the table, that was an amazing horizontal launch. And you say, how fast was that ball initially moving vertically in the y direction as it rolled off the table? And you would say, it wasn't. And you would be correct. It was not moving in the y direction. That's a horizontal launch. Compared to, I think this is not going to work, but hey, compared to this, well, that didn't do exactly what I wanted, but it worked. That was a 2D motion problem. 2D motion problem. It was a projectile. It was moving freely through the air in two directions, but it wasn't horizontal. It went up. It launched through the air at some angle. So it's called an angled launch. So there's two types of projectile motion. There's a horizontal launch, and there's an angled launch. Angled launch is projectile, and projectiles are 2D. So it's 2D projectile angled instead of 2D projectile horizontal. It can't be both. It cannot be both horizontal and angled. It's one or the other. And in an angled launch problem, the object is thrown. I put thrown because it doesn't have to be thrown, but it's thrown at some angle. It went off of a ramp. But it's not horizontal. That's the key. Now, very conveniently in our physics problems, in a horizontal launch, they'll give us some information, like a car drives off a cliff. Like Johnny's driving down the road, and he looks away for just 1 second, and he was going at 55 miles per hour as he drove straight off the edge of the cliff. They, of course, would tell us the speed that Johnny drove off the cliff. But he's got airbags and seatbelts, and he's perfectly fine. Don't worry, everyone. And they can tell us all that stuff, right? But they very conveniently tell us the speed. Same idea with an angled launch. Okay, and we could say a ball is thrown at 30 degrees, but we'd often say like a ball is thrown at 10 miles per hour at 30 degrees above the ground. And in this case, it's not really a number you're going to fill in. It's more of a you don't put a number in. So if it was a horizontal launch, we say it's equal to 0. If it's an angled launch, we don't put a 0. We really just leave it blank. And it might be given, or maybe we're solving for it. Now, on the board, I have a couple of quick examples. So if I were to take this racquetball, and I were to go to a Brewer game, and I go to one of those pitching things, and you pay them like $50, and you get like 3 baseballs to see how fast you can throw the ball. It's not really $50, it's a lot. And back in the good old days, lined up, I could really throw the heat. I could get like 45 miles per hour. Okay, I could be like, oh, shoulder a little tight, but yeah, that's about all I've got. Okay, so I could throw it perfectly flat. Now pretend that this arrow is actually slightly down. Pretend that this is perfectly flat. We actually could go through and we could break this problem into 2 dimensions. We could say, well, of that 45 miles per hour, how much of that 45 miles per hour was going flat? All of it. And how much of it was going vertically? We'd be like, well, none of it. It's a 1D motion problem. Okay, now what's really going to happen is as soon as we release that ball, it's going to go, and it's going to become a horizontal launch. Okay, but we can look at the speed of that ball, and we can say, well, it was a horizontal launch. None of that speed, that 45 miles per hour, was actually talking about vertical speed. It was all horizontal. One of my favorite pitches back in the Little League, no one ever hit it, by the way, is I took that ball and they thought I was going to throw it, and I went, whoop, And no one ever hit it. I don't know why. Went straight up in the air, 45 miles per hour, and it hit me in the head because it was so perfectly straight up. No. And we could look at that pitch and we could say, hey, of that 45 miles per hour, none of it went horizontal, which means it's not the best pitch. But all of it was vertical. So we really could break it into its two components. It's just a 1D motion problem, so there's not really a point in doing it. However, if I was an outfielder and I had to get the ball in from the outfield, I can't throw a line drive from center field to the catcher at home plate. I got to give it some angle. And the reason I can give it some angle, I give it more time in the air. But if I were to throw it at some angle, we could call it theta, 45 miles per hour, then some of that 45 miles per hour is going to be in the x direction. I made up numbers of 30. And some of that's going to be in the y direction. Again, I made up numbers of 20. And it's sine and cosine functions. It's trig functions. And you might say, but Mr. Davies, in one of the first days of school, you said the difference between conceptual physics and traditional physics is the math, and we don't do trig functions. You're right, we don't. Doesn't mean we can't do angle launch problems. The way we do angle launch problems are slightly different. Okay, in a traditional physics problem, let's say a ball is thrown at 30 degrees at 15 meters per second. Okay, and then they do the trig functions for it. For us, it'd be a ball is thrown at some speed such that the horizontal component of velocity is 15 meters per second, and the vertical component is 10. So I can give you these, I can do the trig for you to do these angle launch problems. Okay, so we aren't doing trig, don't worry. And we don't do a lot of them, but we do some of them. There's a special type of angle launch problem, and it's a delta y is equal to 0 problem. And almost every single thing on this delta y is equal to 0 problem is the same as the delta y is equal to 0 problem on our 1D motion sheet. Now what we're talking about is we're talking about a ball, so we're talking from the floor to the floor. So it goes like that, like that. It started on the floor and it ended on the floor. Okay? It's an angle launch. It's a projectile motion now. Okay? It's a 2D motion problem. Compared to before, our 1D motion problems were more like that, right? It went straight up and straight down. Now we can do trying to the iPad. That was probably a poor choice in retrospect. Good thing to miss. Okay, so that's a projectile motion angle launch. Delta y is equal to 0. And in a delta y is equal to 0, the object starts and ends at the same height. My final velocity in the y direction is equal to the opposite of my initial velocity in the y direction. And the total time is 2 times larger than the time it takes to get to max height. It's the exact same thing that we filled in. Delta y is equal to 0 for our max height problem. So we really have 2 types of 2D motion. One type of 2D motion, in summary, is that. Okay, it's moving through both the x and the y problem simultaneous. That's a 2D motion problem. The other type of 2D motion problem that we have is called a projectile motion 2D motion problem. And in a projectile motion, 2D motion problem, am I in the screen?
Yes.
All right. Go about where? Here? We're still in?
Yeah.
Okay. Okay, we can also do a 2D motion projectile like this. Okay, that's a 2D motion problem. It's moving through the through the x and the y simultaneous. It's a projectile motion problem. Got a different input. Okay, it's a 2D motion problem, but it's moving through the air freely in the x and y simultaneously. The thing is, the motion in the x is independent of the motion in the y. The acceleration due to gravity has no effect on my speed in the x direction. bowling ball holder. Okay, so that's your 2D motion problem tips. I would like to talk briefly about tomorrow's virtual day assignment. So tomorrow's virtual day assignment consists of, it's linked in tomorrow's virtual day agenda. But ultimately what you're going to do is you're going to get to this. Okay, so this is the assignment. So if we go to modules, you go to tomorrow virtual day, there's 2 things. You're going to watch a 5-part, about 21-minute Mythbusters video. Okay, and when you click here, it should take you automatically to this playlist that has 5 videos that kind of should autoplay for you. Okay, the actual assignment is there's a Google form that you're going to go through and you're going to fill in as you watch or after you watch. So once you get to the assignment, again, this link will get you to the 5 videos. I feel like the volume's a little on the low side, but I think it should be okay. And then there's a form that you're going to fill out. And again, there's the list to the 5 videos again. Fill out your name, fill out a period, and then there's a series of multiple choice questions based straight out of the video, just to kind of make sure you're watching. It's Mythbusters. Mythbusters are good. They're entertaining. They do some good science. And you'll see some things with slow-mo cameras that they use the cameras to measure time. You see some scales and grids measured out, and that's so they can look at their camera shots and they can measure different distances based on the scales that they do. Okay, so it's about 21 minutes worth of videos, all 5 parts, and then I don't even remember, there's not that many questions for you to answer. Take a screenshot of your final score, make sure the score is on there, submit that as evidence that you watched the video and you answer the questions. That's your virtual day assignment. It's talking about the time it takes if you were to take a bullet, oops, sorry, gotta point my gun in a safe direction, always point your gun in a safe direction. Treat it as if it's loaded. Okay, so if we take a gun and we fire a bullet, the bullet comes shooting on the ground. Horizontal launch, perfectly flat to the ground. The idea is, the myth that they're testing is a bullet fired out of a gun compared to I take a bullet and I drop it from the exact same height, which one's gonna hit the ground first? And that's the myth they're trying to test. The classic physics experiment says they're gonna hit the ground at the exact same time, but doesn't. And that's what that video is about. Okay? So with that said, I think I don't have anything else I need to tell you. If you have any questions, please let me know. But yeah.